Hey everyone, welcome to our next section. We finished up our kinematics unit and it's time to move on into dynamics. And so we're going to start dynamics by going through forces. I've got a few definition terms just to kind of cover up front, things that may pop up throughout the lesson that we can just kind of discuss and go through. So just like the other ones, I encourage you to copy down notes along the way, or whichever way that you learn best to kind of be able to retain the information that's here. So when we start to get into forces, there's some terminology here that we have to go through. So we can talk about things like a force, for instance. So a force is a push or a pull, and forces can happen in a variety of ways. Magnets can be used as a force in terms of having magnets that have the same charge. They may repel each other, give things a push. They can also have opposite charges and attract. And if we can use that idea of magnets, then we can also think of things on a small scale like protons and electrons doing the same thing. And then we can also think of things in our everyday life that basically enable us to function the way that we do. So anytime that we ever pull on an object, push an object, we're using a force to do it. And so there are fundamental forces, and forces are classified basically into four categories. We have gravitational forces, electromagnetic forces, a strong nuclear force, and a weak nuclear force. So the next few slides are just going to be kind of explaining each of those in a little bit of detail. So the gravitational force is a force of attraction between all objects. Normally, if there's a very large discrepancy in mass, then you'll tend to notice a very large gravitational force that would accompany that. But every object has some sort of gravitational force to it. Then we have an electromagnetic force, which is caused by electric charges. And so if you've done anything with static electricity before, or have ever shocked yourself on anything, you're experiencing electromagnetic forces. Then we have a strong nuclear force. It holds protons and neutrons together inside the nucleus of an atom. So we start to get down to the smaller scale with the final two, and understanding kind of the protons and neutrons are inside the nucleus and electrons are buzzing around on the outside. So the strong nuclear force is what's required to hold those protons and neutrons together in the nucleus. And then we have a weak nuclear force, which is responsible for interactions involving really elementary particles, such as quarks and muons and that kind of stuff. And so altogether, we have these four fundamental forces or fundamental interactions that basically attribute every force that we can experience and know would come from this kind of idea. So a force is a vector quantity, which means that it has a direction as well as a magnitude. And to keep in mind that magnitudes are positive values. So if you're getting an answer that is telling you that something is negative so much force, then that just indicates it's positive in the opposite direction. So just keep in mind that all the stuff from vectors from our kinematics unit can kind of pop back into this unit as well. So all forces that have been found so far can be classified into the four fundamental forces that we know. Okay, that gravitational force, electromagnetic, strong, and weak nuclear force. So to start off our gravitational force, gravitational forces don't just apply to the things here on Earth, but they also apply to much larger objects, stars, planets, moons, holding them together and controlling their motion. So gravitational forces act on two objects even if they're not touching one another. So even something like light can obey a gravitational force, which is, in terms of space, one of Einstein's famous experiments that he was able to contribute when he's trying to show that light actually bends around large gravitational forces such as planets and black holes and that sort of thing. So electromagnetic forces, they include both electrostatic forces like static electricity and magnetic forces such as force that affects a magnetic compass. They can exert an attraction or repulsion the same way that we understand how electrons work with protons and electrons and north and south poles on magnets. So they're responsible for holding atoms together. They make diamonds hard and they make cotton weak. they're responsible for how elements are constructed and how their properties behave. So most common forces are electromagnetic in origin, and I've got a YouTube linklets there that I'll share on the website as well. That's just kind of something a little bit extra, but is definitely eye-opening when you consider all the pieces that we've talked about so far. So I encourage that you pause the video and go watch that one, and then just come back to here when you're done, and we'll continue on. So our next one is a strong nuclear force. It holds our protons and neutrons together in the nucleus. So protons naturally would want to repel from inside the atom, which is the reason why there's so much energy given off when atoms are split. They only work when objects are really close together, and it's stronger than the electromagnetic force. So our strong nuclear force, we can see here, it says binding protons in atomic nuclei. Positively charged particles naturally want to repel each other, and it takes an extreme amount of force to want to hold those protons together. The strong nuclear force overcomes the repulsion between the protons to hold together atomic nuclei. So without the strong nuclear force, complex nuclei cannot form because they would all want to push apart. So enormous energy is released as gamma rays and neutrinos when the strong nuclear force is broken between protons and neutrons. So we get a massive amount of energy because there's such a big buildup there. Then our last one is a weak nuclear force. And so weak nuclear force is noticed only at extremely small distances. And without the weak nuclear force, we wouldn't be able to tell how old things are, such as carbon-14 dating or uranium-lead dating, based on what it is that we're trying to find out how old that object might be. So the weak nuclear force converting protons into neutrons. So when two protons collide and fuse, we get this disruption in the weak nuclear force, and it emits a positron and a neutrino, which converts one of the positively charged protons to a neutrally charged neutron. Without the weak nuclear force converting protons into neutrons, certain complex nuclei cannot form. Now there's a lot of terms there. You do not need to know for Physics 11 for a starting part, but basically the weak nuclear force is responsible for converting protons into neutrons and other smaller particles as objects start to decay, which is one of the reasons why we mentioned this idea about carbon-14 dating and uranium-lead dating, because that function of that dating process is due to the amount of decay in our protons and neutrons. Okay, so our four fundamental forces. So then there's a little question, what is one force that we're all experiencing right now? So you sitting in your chair and your desk right now, listening to this or watching the video, the one force that we're all experiencing right now, something that's kind of keeping you steady, keeping you upright, and not, floating away. So hopefully the one force that you're thinking of is gravity. So gravity is that one thing that keeps us all where we are right now and all kind of stuck to the planet. So what about the books resting on your desk or the pencils? Are they experiencing gravity right now? And yes, the answer is yes. So every object experiences some form of gravitational pull. So a little bit more terminology to run through. We have the normal force, and this one is one that's really important because people often confuse this with what we're going to call the net force. So we need to get this definition kind of understood and straight. So the force perpendicular to the surface of the object in contact. So a normal force involves two objects that are in contact with one another, and it's perpendicular to the surface that the object is sitting on. So if we have a ramp, for instance, and we have an object sitting on a ramp, then the perpendicular force will go away from the ramp at a right angle. So it needs to be in contact with one another. It's a type of force, but it involves contact, and it always goes perpendicular to the surface. So if an object is just sitting flat on a surface, that means that the table or the desk or whatever surface is kind of going horizontally. Perpendicular to that would say the normal force is going upward. Then we have a frictional force. It's a force between objects in contact and parallel to the contact surface. So we have some force that's trying to push an object going in one direction, and we have a frictional force in the other direction causing that object to want to slow down. And so only when we overcome the frictional force do we actually get forward motion. Then we have tension. Tension is anything force-wise that's exerted by things like strings, ropes, fibers, cables, anything that basically has some sort of connection to it that's causing it to pull in one direction. And so you can see the crane picture here. It's got a rope coming down. The ball's hanging off of it, and so there's a tension force pulling upward on that cable, keeping that ball where it is. So the normal force, the force of friction, and the tension are all contact forces. So in other words, they exist only when objects are in direct contact with one another. So if two objects are not touching one another, I have no normal force, I have no force of friction, I have no tension. And really, when we start to think about objects that are not in contact with one another, that's when I start to think about things like gravitational pulls, magnets, that kind of stuff. And so, but if ever objects are in contact with one another, that's where we have a normal force, a frictional force, and tension that could be applied. So they're caused by this interaction of particles on contact surfaces and are therefore a result of electromagnetic force. And if you've watched that YouTube video, you kind of get this idea of the gap that could be between two objects that becomes really, really microscopically small the more force that's applied between them. And certain objects have greater ridges than other objects have, and so it takes a little bit more force to overcome the frictional force that would be there on those objects. So, measuring force, the unit of force is called a Newton, and aptly named from Sir Isaac Newton, who accomplished quite a bit in his lifetime in terms of a lot of different things, from physics to math to finance and business. He dabbled in a lot of different areas in his life and was able to accomplish quite a bit. So, capital N stands for a Newton, so that's a unit that we're going to use. The same way that you would call a kilogram kg, we call a Newton a capital N. And so a Newton is a derived scientific international unit, which basically is a metric unit, and it can be expressed in terms of kilograms, meters, and seconds. And so what we kind of say is 1 Newton is equal to 1 kilogram meter per second squared. So that's what defines what a Newton is. And so notice the units that are in here. We're dealing with a mass unit, we're dealing with some sort of distance, and we're dealing with some sort of time. Okay, kilogram meter per second squared gives us a Newton. Oh, and I should add before I move on, if you want to see a Newton scale, just let me know if you're here kind of watching the video, and I'll certainly bring one over just so you can kind of get a sense about how much force or how much pull is in a Newton. So, our last slide, drawing force diagrams. So there's two types of force diagrams that we're going to use in the course. One of them is a system diagram, so it's a sketch of all the objects involved in a situation. So a system diagram, let's say we had our picture here with our rock climber, and then in the middle would be our system diagram. So we'd have the idea of the outline of the person. We don't really need the rocks or the background or anything, so it just gets the person, the thing experiencing the force, and then it starts to outline all the forces that are there. So we have the pull of gravity on the person, bringing them down, so the force of gravity. We have the foot on the cliff, so you can see the arrow that's coming over here, the push of the cliff. We also have the friction of the cliff between the foot and the mountain, and then we also have a tension force with the pull of the rope. So there's many different forces that are acting in this scenario. A system diagram kind of shows all of those forces in something that you could look at. Now the bottom one, or the one on the right hand side here, is a free body diagram, and these ones only use objects being analyzed. And so keep in mind that vectors, and from some of our other worksheets that we know, vectors can move, and so we could actually take all of these frictional forces and isolate them to one point. So only the object being analyzed is drawn. It uses arrows to show all the forces acting on the object. So notice here we have a central dot. That dot basically represents the force of the scenario. And so we have the cliff pushing off on the man. So we have our normal force coming directly outward because there's contact right here. So we have a normal force pushing out, right? Push off the cliff. We have a force of gravity on the person pulling down. And then we have two upward forces, the green and the brown arrow that are here, a force of friction and a tension force. So we can see force of friction, a tension force, a normal force, and a gravitational force, or the force of gravity. So we have a free body diagram on the right, we have a system diagram in the middle, and we're going to be kind of working between both of those throughout this first assignment and moving into our first area on dynamics. So you now kind of have everything that you need to know for our first assignment to go through, as well as the lab activity that kind of accompanies that afterward. So if you have any questions, let me know.